Good morning. Thank you. All right. Cosmology the fourth. Yesterday, the lecture had two main parts, two main pieces of content. The first one was formation of light elements in the early universe. And we saw that it takes a few minutes for the universe to produce light elements up until lithium-7. And further fusion is not possible in that time, essentially because there is no stable nucleus with an atomic weight of 8. Right? All right. This had important, or this allowed important conclusions. We saw that this is so early in the evolution of the universe that the radiation density dominates everything. Right? And this means that we do not need to know the detailed contents of the universe at that time. Rather, all we need in order to understand the ratios of the abundances of the light elements relative to hydrogen is one parameter, which is the ratio of the densities, number densities of photons to the baryons. And we saw that the measurements of the deuterium abundance, essentially, but also of other light elements, tell us a certain value for the ratio between the baryon and photon number densities. And since we know the number densities of the photons from measurements of the cosmic microwave background, we can conclude that the baryon density in the universe can amount to at most approximately 4% of the critical density. Right? This was the main conclusion from that. At the same time, I would like to emphasize that these calculations of the element abundances in the early universe and their measurements provide one of the earliest tests of the Friedmann-Robertson-Walker model, or the standard cosmological model, because they provide a measurement point as early as a few minutes after the Big Bang. Okay. So that was that, and then we looked at cosmic structure formation. I told you that if we study the linear evolution of cosmic structures, we can simply use the Newtonian hydrodynamic equations. Right? So the equation of continuity, the Euler equation, and the Poisson equation for Newtonian gravity. And if we do that, we saw that structures in the universe grow essentially at the same pace as the universe itself grows. Right, which immediately leads us to the conclusion that by far the most matter in the universe must be contributed by something which is not interacting electromagnetically, because otherwise the temperature fluctuations in the cosmic microwave background should be a factor of 100 higher than they are observed. All right. And then we were thinking about the statistical properties of cosmic structures, which are described by either a correlation function in configuration space or a power spectrum in Fourier space, which are equivalent to each other. And we saw that there are very simple arguments that lead to a prediction for the shape of the power spectrum of cosmic structures, which seems in fact to be realized. Right? One more example for the simplest assumption that seems to be realized in cosmology. All right. Do you have any questions up to this point? If not, then I would like to go back again and speak about the structures in the cosmic microwave background, right? So as to understand why they are so important for cosmology, what the driving mechanisms are that give rise to these fluctuations, and what we can conclude from them. All right, structures in the CMB. So the most pronounced structure in the CMB is the so-called cosmic dipole. Right? Remember what we said about isotropy. Right? You can expect to observe isotropy in the universe only if you are in the rest frame of freely falling observers in the universe. And since we are not, we are moving with respect to the rest frame of the cosmic microwave background. And this means that in the direction of our motion, we see slightly blue-shifted photons, and in the opposite direction, we see slightly red-shifted photons. So this imprints a dipolar pattern on the cosmic microwave background. This has nothing to do with cosmology, of course, right? This is the cosmic dipole as measured by the WMAP satellite. It shows you where we fly, right? Where we fly, in what direction we fly. It shows you the amplitude of the dipole, tells you our velocity with respect to the cosmic microwave background. But of course, if you want to do cosmology with the cosmic microwave background, we just have to remove the signal. All right, so let's get rid of it. Then, as we saw yesterday already, and this can't be repeated often enough, density contrasts in present-day structures near 1 or higher imply that we should have temperature fluctuation in the cosmic microwave background on the order of 10 to the minus 3 or higher. And this is, of course, where they have been sought in the first place. In 1965, the cosmic microwave background was detected, and then, of course, immediately people started looking for fluctuations in the cosmic microwave background. And they did not find them. Right? And around the time when I did my PhD, there was a real crisis, the feeling of a real crisis in cosmology, right? Because yet another experiment had found nothing, right? No fluctuations in the cosmic microwave background. And then Jim Peebles Jim Peebles published the decisive idea. Right? He said, all right, this can all still be understood if we assume that most of the matter in the universe is not even electromagnetically interacting and therefore does not leave a strong imprint in the cosmic microwave background. And he predicted, I think in 1987, that from that hypothesis you would expect temperature fluctuations, relative temperature fluctuations on the order of 10 to the minus 5. And this was ultimately where they were finally detected. All right, so we have temperature fluctuations on the order of 10 to the minus 5, which is not a lot, but this is a great advantage, in fact, because obviously these fluctuations are in the linear regime, and therefore with relatively simple physics you can understand them. This is the latest picture, and probably the decisive picture of the cosmic microwave background temperature fluctuations. When I say decisive picture, because it was taken by the Planck satellite, with an angular resolution of 5 arc-minutes at best. And as you will see later, we do not expect that there should be any smaller structures in the cosmic microwave background, and we don't see any. Right? So this seems to be the definitive map of the cosmic microwave background temperature fluctuations. What we do with that is a different business, right? But if you look at it, you see coherent structures. Right? So these are not just speckles, but these are when you have a speckle with a high temperature fluctuation, there's a higher probability to find a high one nearby. Right? So there are correlation properties in these temperature fluctuations, and of course they carry the decisive signal that we are after with these observations. All right. What do we do with them? Well, of course, the first thing to do with if you want to analyze a random field is a Fourier transform. But then, of course, on the sphere you can't do a Fourier transform. You have to do something else. You do a harmonic analysis with the help of spherical harmonic functions. And to illustrate that, I've taken another object here that you might recognize and decomposed this into spherical harmonics. Right, so this is the dipole. What does it tell you? There's a lot of water on one side and a lot of land on the other. Aha. Quadrupole. Antarctica shows up. Hexadecupole. I don't recognize much anymore, right? But now America appears, right? Okay, now the right column tells you, the right column shows you, no, that's a different picture than I wanted to show you. Anyway, these are just increasingly higher orders of multipoles, and this is what you get if you add together all of them up to this point, right? So this is multipole order L equals 2, 3, 4, 5, 6, 7, right? And this is the sum of all of them together. All right, we do the same thing with the cosmic microwave background. Essentially, imagine we are just doing a Fourier transform. Right? So, as we did with the cosmic structures, we can then, of course, determine the variance of the temperature fluctuations in Fourier space, or rather in spherical harmonic space, and this will be the power spectrum and so on, so the terminology will be exactly the same. What do we expect? Well, first of all, we have an equation for the temperature fluctuations which very closely resembles the density perturbation equation that we saw yesterday. Right? Imagine or remember this equation we had for the density contrast, right? Which looked like a damped oscillator equation. This is an equation for the relative temperature fluctuation, which couples the temperature fluctuations to pressure perturbations in the gas. Right? There should be a CS there, and sound speed rather than the speed of light. This comes from the Poisson equation. Right? These are the potential fluctuations multiplied by a minus k square, which comes from the Laplacian of the in the Poisson equation. And this is an additional equation which we need to take into account because the potential may change due to cosmic structure growth, while the gas in the potential wells undergoes acoustic oscillations. Right, so we need to take simultaneous changes in the potential into account. All right. Now you play the same games as we did yesterday. Right? Suppose k is small. That's very convenient because then you can just drop these terms. Right? So these are the very largest terms. And then you see, all right, the temperature fluctuations will then just reflect potential fluctuations and nothing else. Yeah.
Are the variables with head averaged also? Because in the first definition of theta you haven't included the head.
The hat should just signal the Fourier transform. Sorry. All right. So for small k, temperature fluctuations are just driven by potential fluctuations. So essentially what you see there is the imprint of potential fluctuations on the temperature of the photons. In other words, what you see there is the so-called Sachs-Wolf effect, that photons which are released from a potential sink have to climb out and thus lose energy. And photons which run down potential hills when they are released gain energy. This is the whole physical effect behind this. And then if you go to larger k, you get a driven oscillator equation. Right? Suppose you can now ignore this term here. Right? Then, if these terms dominate, these two terms would simply be an oscillator equation. Right? They give rise to acoustic oscillations in the gas, which are reflected by the temperature fluctuations. But then this term drives this oscillator equation. And so you have a driven harmonic oscillator equation there, and the driving force is, of course, the gravitational force. All right. Now, you can combine the temperature and the potential fluctuations, and then find an oscillator equation for this combined quantity and solve it. Right? And these are the acoustic oscillations that we expect to see in the cosmic microwave background, where this quantity here, right, the speed of light, sorry, it was the speed of light because the factor of 3 down there, I have to explain this a bit. So the speed of light divided by the square root of 3 is the sound speed at that time. This is because the pressure in the gas is dominated by the photons. And the sound speed is just a derivative of the pressure with respect to the density. And if the pressure is dominated by the density divided by 3 behavior of the photons, right, then the speed of light is just, the speed of sound is just the speed of light divided by the square root of 3. So that's the sound speed. That's the recombination time. So the time that we calculated yesterday, approximately 380,000 years after the Big Bang. Right? So this again sets a horizon scale, like we discussed in the first lecture on Monday, but this time it's a sound horizon. Right? It's the distance that a sound signal can cover in the time between the Big Bang and the release of the cosmic microwave background. All right, and on scales smaller than that, you will see acoustic oscillations. On scales larger than that, the material cannot oscillate, right? Because there is no causal connection between across larger fluctuations larger than the sound horizon. So that sets a definitive scale. On scales larger than the sound horizon, the Sachs-Wolf effect will dominate, and the only temperature fluctuations that you will see in the cosmic microwave background are caused by potential fluctuations. And then on scales smaller than the sound horizon, acoustic oscillations will set in, and you will see an oscillatory pattern. But that's not all. That's not all. Now remember what we saw yesterday? Tuesday, I think. Anyway, you remember that we talked about the finite time that it takes for the cosmic plasma to recombine. Right? This was this time scale of about 40,000 years that it takes between the onset of recombination and the end of recombination. I also showed you this approximately Gaussian curve where I said this is the result of a poll among photons, among CMP photons. Right? If you ask them, when did you last meet an electron, this would be the distribution of answers. Right? So now, remember, these cosmic microwave background photons are not released from a spherical surface surrounding us, but from a spherical shell surrounding us with a finite width. Right? So the photons stream out of a shell of finite width and then arrive at our place. But while the cosmic plasma is recombining, the mean free path for the photons is increasing, right? Which means that photon diffusion sets in. Right? The length scale over which photons can diffuse is increasing while recombination proceeds. So as we look into this recombination shell, we will see the onset of photon diffusion as well. And photon diffusion gives rise to wiping out, the partial removal of fluctuations on very small scales. Okay, so the onset of diffusion wipes out part of the fluctuations. All right, now what's that scale? Well, that's the diffusion mean free path. Right? This just comes from a theory of the random walk. If you walk by n steps randomly, the standard deviation of your walk will be root n times the mean free path per step. Mean free path per step is given by the electron density in the Thomson cross-section. And it's Thomson cross-section, not Compton scattering, because of the energy scales. Right? It's long in the in Thomson scattering regime. All right. So the number of collisions per unit time is given by this quantity. Right. Also the electron density times the Thomson cross-section times the speed of light, and so on. And therefore, it's very easy to calculate the square of the diffusion length. Right? And so you can calculate this, and then you find above which wave number or which multiple order, or in other words, below which scale you expect to see the onset of photon diffusion, and thereby the suppression of fluctuations in the microwave background. This effect is called Silk damping, after Joe Silk, who first discussed this. So these are the three effects that we expect to see in the cosmic microwave background power spectrum. Right? So like yesterday, this is a power spectrum, so it's a variance in Fourier space in quotes, because actually it's spherical harmonic space, but this doesn't matter principally. So this is the multiple order. And the rule of thumb is the angular scale, or the multiple order is the angle in radians divided by pi. Right. Okay. So here you see the Sachs-Wolf effect. Right? The structure caused by the potential fluctuations, which is reflected by the temperature fluctuations in the microwave background according to the Sachs-Wolf effect. Then, on a scale corresponding to the sound horizon, and approximately here, you see the onset of acoustic fluctuations, right? In other words, sound waves. So what do you see here? Well, it's the fundamental sound mode of the universe at that time. And of the universe, of course, means of parts of the universe whose size is set by the sound horizon. Right? So that's the fundamental mode. And then, of course, you see the overtones. And then you see the onset of silk damping, right, which leads to an exponential damping of this curve due to the onset of photon diffusion on small scales while recombination proceeds. All right, the quantity that is usually plotted here is not really the power spectrum itself, but L times L plus 1 times the power spectrum. So this corresponds to the spectrum K cubed times power spectrum that we looked at yesterday. Right? It's the number of modes times the power spectrum. And this is just to emphasize these interesting parts here on small scales. All right, these are the main things. This is these are the effects that shape the appearance of the cosmic power spectrum. And as you see, conceptually they are relatively easy to understand. The actual calculation is more difficult, but this doesn't concern us here. All right, now why is this power spectrum so interesting? I plot here 3 power spectra with 1 parameter changed, so that you can see what effect this would have on the cosmic microwave background power spectrum. So the blue curve in the center has been calculated with a cold dark matter density parameter times h square of 0.12, right? So this corresponds to a cold dark matter density parameter of 0.25 roughly. And then I've changed this density parameter by 10% up and down. Right? If you change it down, or if you lower it by 10%, you get the orange curve. And you see the curve is now above the blue curve. Right? So this increases the fluctuations. Why? Because now the oscillator has to drive less matter. Right? The inertia of the oscillator is reduced. Right? All right, then if you increase the mass, increase the matter density by 10%, you get the dark red curve, and correspondingly you lower the power spectrum. This is one of the effects of one of the cosmological parameters. Right? Now, suppose I would have played with the baryon density parameter, then the reverse would have happened. Right? And this is a very interesting thing, because the baryon density is responsible for driving the fluctuations. Right? They give that's the counteracting part to the inertia. Right? So if you increase the baryon density, you have the reverse effect on the power spectrum. And this means that looking at this curve, you can not only measure the total mass density, but you can distinguish also between the mass, between the inertia of the mass and the driving part of the mass, right? The pressure. All right, so this contains a lot of very valuable information. All right, there's another point. I told you that Thomson scattering is the relevant scattering process between the electrons and the photons, and the reason is that the energy scale is of course way below what you would need in order to have Thomson scattering. So Thomson scattering is the right approximation, but Thomson scattering is direction sensitive, right? So let me show you this picture right away. So suppose you have here a single and lonely electron, which is green, as everybody knows, and you irradiate this this electron with unpolarized radiation coming from your perspective from the left. Okay, so here it comes, and the 2 rods are supposed to be of equal length, and this indicates that this radiation is unpolarized. Right? All right, but now this part of the electric field of the incoming light will accelerate the electron along the line of sight, and therefore you won't see a signal from that, right, due to the radiation characteristic of the Hertz dipole. So all you will see is the result of the electric field driving the electron perpendicular to the line of sight. So this is what you will see from the light that came in from the left. Now we do the same thing with also unpolarized light shining on the electron from the top now, but with a smaller intensity. Right? So there the bars are shorter than the blue ones, and the result is going to be this. Right? If you look at the ellipse that these two rods are now forming, you see that the net result is an effective linear polarization by the scattering process if you illuminate the scattering electron in a pattern like this. And this is a quadrupolar pattern, right? So if you imagine you have the same intensity coming from the left and from the right, and the same but lower intensity coming from the top and from the bottom, you see that the irradiation pattern falling on the electron is quadrupolar. Right? So the quadrupolar part of the cosmic microwave background intensity fluctuations is giving rise to linear polarization. So we expect from this consideration that the cosmic microwave background should be linearly polarized to approximately 10%. What does this mean? This means that if you look at temperature fluctuations on the order of a microkelvin, sorry, on the order of 10 microkelvin, right, 10 to the minus 5, then the polarized part of the intensity should be on the order of a microkelvin, linearly polarized. Okay. So that's another important prediction of the relatively simple scattering process, and something that we will have to observe, right? It has been observed, by the way. This is the so-called E-mode polarization map produced by the BICEP 2 experiment on the South Pole. And for the moment, it's sufficient for us to just see the polarization pattern and how it is correlated with the temperature fluctuations that are underlying this picture in the color scale. Right. So, of course, there are the expected correlations between the temperature fluctuations. There are similar correlations between the polarization fluctuations, and of course there are cross correlations between the two, right? Because essentially the physical driving mechanism is exactly the same. All right. So much for that. Now, this is the first venerable satellite that observed the microwave background. Of course, not the first experiment to observe the microwave background. Right? This has happened way before. But this was the first experiment carried out from space, and was the first experiment with which the temperature fluctuations in the microwave background were in fact found. It had an angular resolution of 5 degrees. Sorry, 7 degrees. 7 degrees. This is not much. Right? So it could observe large-scale patches in the temperature fluctuations. But it was enough to see them, right? But not enough to proceed to the regime where you see the acoustic fluctuations. Right, so COBE, right, this satellite here, Cosmic Background Explorer, saw the temperature fluctuations in the Sachs-Wolf Plateau, but could not proceed into the acoustic fluctuations. All right, that was 1990 to 92. Then several balloon experiments were launched. The problem with these observations is that the atmosphere, because it contains water, is absorbing the incoming microwave radiation very strongly. Right? So you have to go to places where either you have little atmosphere, in space, for example, or you have to go somewhere where there is very little water in the atmosphere. Right? So, for example, to the South Pole. You can combine this, right? You can take a stratospheric balloon, which carries the experiment into heights where there's little atmosphere, in a very cold environment where there's very little water, and then you can observe. So these two experiments here, Boomerang, which fortunately did in fact come back, and Maxima, observed much smaller patches of the microwave background. Right? Kobe observed the full sky. Those balloon experiments observed a very small section of the microwave background. But they were the first to see, in fact, the acoustic oscillations in the power spectrum of the microwave background. And from then on, it was clear that something is wrong. It was clear that something is wrong. The point is this. If you look at this power spectrum and you recall where this peak is coming from, right, then you immediately see that the location of the peak here tells you the angular scale corresponding to the sound horizon in the early universe. We know the physical scale of the sound horizon. Right? It's just the speed of sound times the time until CMB recombination. So that's approximately 380,000 years times the speed of light divided by the square root of 3. That's not a complicated calculation. So that's the physical size of the sound horizon. The angular size you can measure, right, from the location of this peak. Now, if you compare the two, you can calculate the spatial curvature of the universe. Let me draw a picture for that. So this is the sound horizon, right? That's a known physical length scale. And now we down here, right, see this length scale under a certain angle. How do we do this? Right? Imagine we propagate light rays from the ends of this meter stick here to the observer. Then, of course, what we expect is this. Right? And then we will see this physical scale under a certain angle here. But of course, that's the expectation in flat space. Right? Then you would have straight lines propagating from the observer to the ends of this meter stick. Doesn't need to be, right? The light rays could run like this. This happens if the universe is positively curved. Okay, because then light rays converge instead of increasing their relative separation linearly. This linear increase of the separation between the light rays, that's typical for flat space, but behavior like this would be typical for positively curved space. So then you see, if that would be the case, right, if space would be positively curved, then you see a much larger angle. And you see the same object under a much larger angle than in flat space. And of course, let's use the same color, but different line type. Let's do it like this. If you did the same in negatively curved space, right, then the light rays would diverge, and the angle under which the same scale appears to us would be much smaller than before. In other words, from the location of the peak in the power spectrum, you can immediately conclude what the spatial curvature of the universe is, right? And then with the first experiments that could see the onset of that peak, it was clear that the peak lies at a position which corresponds to flat space. And that was the problem. Because if you take the budget that we now have for the energy content of the universe, right? We have radiation. Nowadays, doesn't matter. Right? It corresponds to approximately 10 to the minus 4 of the critical density. The baryons, well, they contribute about 4%. Dark matter, well, may contribute about 30%. So in total, we know that the energy budget amounts to much less than the critical density, and therefore space should be negatively curved, right, as we saw in the first lecture. But it isn't. It's flat. And if it's flat, the sum of all forms of density, all forms of matter densities, should be 1, right? 1 in terms of the critical density. So this immediately showed that 70% are missing from the budget. Right now, this was before the time when budget deficits of that size were common. Right, so this was really an effect that disturbed cosmologists very strongly. All right. So we knew at the latest from this point, right, from these experiments, that there was something wrong with the energy budget in the universe. All right. This was WMAP, Wilkins Microwave Anisotropy Probe, which achieved an angular resolution of about 15 arc minutes. Now, if you go back to this power spectrum, the schematic sketch of the power spectrum here, 15 arc minutes are already in the Silk damping tail of the spectrum. But at 15 arc minutes, you do not quite cover the whole range where you expect structures to exist in the microwave background. Right? So WMAP did an important job, but not the full job. And then with Planck, we could finally cover the whole range of acoustic oscillations in the cosmic microwave background well into the Silk damping regime. Right? This is why I said in the beginning, we know from the observations of Planck observations by Planck, as well as from the theory of the cosmic microwave background, that structures smaller than about 5 arc minutes just should not exist in the microwave background. At least not primordial structures. Right? And therefore we believe that what Planck saw is not just one more map of the cosmic microwave background temperature fluctuations, but the decisive map of them. All right, that's the power spectrum observed by Planck. The red points, that's Planck 2015, right? This is the latest data that have been released. The red points are, of course, the measurements. The green curve is the best fitting expectation according to Lambda CDM. Right, to the simplest cosmological model you can construct. It's an extraordinary fit, and it marks an extraordinary triumph for, let's say, simple-minded cosmology. So you can fit this curve with 6 parameters, and therefore, since the curve has a lot of structure, you can determine these parameters relatively well. Yeah.
Just a question, the error bars, why are they going off for large angles?
Yeah, this is because that's the so-called cosmic variance, right? And this is because there's only a finite number of spherical harmonic modes that you can fit on a sphere. And the lower the multipole order gets, the larger these modes become. And the smaller is their number that you can fit on the sphere. So that's the statistical fluctuation because there is only a finite amount of modes that you can fit on the finite sky. And that's called cosmic variance. And in fact, this curve is cosmic variance dominated up to L of 400. Right? So up to L of 400, the error budget is dominated by this cosmic variance effect, right? Not by systematics or instrumental noise or whatever. All right, this is the power spectrum, the so-called cross power spectrum between the temperature and the so-called E-mode polarization. So, in other words, that is what you get when you cross-correlate temperature fluctuations on one part and a fraction of the polarization pattern on the other part, right? As you remember, you get a power spectrum by multiplying the Fourier components together. Now you take the Fourier components of the polarization times the Fourier components of the temperature fluctuation and average them. You get this so-called cross power spectrum. Again, the blue curves, the blue points are the error bars, and the red curve is not a fit. The red curve is the expectation that you get with the parameters fit to the previous curve. Now this is quite something, isn't it? I mean, it's running almost exactly through all these points. All right, so we believe we understand this to some degree. To some degree. The problem are the foregrounds. So let me show you a nice collection of maps. This is also from Planck 2015. These are maps of the full sky taken in the 9 frequency bands that Planck had. There was 30, 44, 70, 100, 217, 353, 400 something, and so on, gigahertz until 857 gigahertz. So this corresponds to a centimeter wavelength, and this approximately to 0.3 millimeters wavelength. Okay? So that's long wave, short wave, relatively. And yeah, what you can see in all these maps is that you see almost everything but no CMB, except in the outskirts of the maps. Right? So what do you see? Well, all these maps are centered such that the disk of the Milky Way galaxy is running along the equatorial line of the maps. So what you see is mostly galactic signal, right? Local foreground. And this part is radio emission, which mainly comes from relativistic electrons gyrating in the magnetic field of the galaxy. And this radio emission has a falling power law, right? So this becomes less and less intense as you move on in frequency. At the same time, you see a different signal coming up. Right? That's from warm dust in the Milky Way. And the warm dust is really a nightmare, but for more reasons than that. So you see, there's one dominating intensity component coming down, another one coming up, so there's a window in between around 100 gigahertz, right, in which the observations are best possible. And of course, you have to get rid of all of that. You have to get rid of all of the foregrounds. Now, how would you do that? Well, the best way of doing that is to do these observations of the full sky in the microwave regime in as many frequencies as possible. And you ask, what is the largest possible signal that I can extract from all these maps which corresponds to a Planck spectrum? Right? Because all the foregrounds do not have a Planck spectrum. But we know very well since COBE, I showed you the spectrum yesterday, that the cosmic microwave background does have a Planck spectrum. So essentially you maximize that part of the signal that corresponds best to a Planck spectrum across all the frequency channels. You call the rest foreground or garbage or whatever your intentions are. And then you can separate, first of all the foregrounds from the background. And then, of course, if you have an idea of the individual spectra of the foreground components, then you can still split up the foregrounds into different components, such as the radio emission, the dust emission, and so on. Right? So this is a complicated process, and it needs a large frequency coverage by the observation in order to extract the primordial microwave sky. Let me show you one example which is particularly interesting. This is, on the left-hand side, you see a galaxy cluster. Well, a sketch of it. Right? And as you may remember from the picture of the Coma galaxy cluster that I showed you, galaxy clusters contain hot gas. Right? And the temperature of the gas is on the order of 10 kiloelectron volts. We see this by the X-ray emission of that gas. So here comes a CMB photon. What's the energy scale of that CMB photon? Well, we saw that recombination happens when the temperature is about 0.3 electron volts. So now we are a bit later in the cosmic evolution. Scale factor has grown by a factor of 1,000. So now the electrons have an energy of a typical scale of 0.3 milli-electron volts. and they enter a regime where electrons are running around with a typical energy of 10 kiloelectron volts. So if any of these electrons meets a photon, inverse Compton scattering will happen. Right? And the photon will leave the galaxy cluster with a much higher energy than it entered the galaxy cluster with. In other words, galaxy clusters scatter CMB photons from lower to higher energies. So if you observe the cosmic microwave background through a galaxy cluster, through the hot gas in a galaxy cluster, and you observe at low frequency, you see galaxy clusters as shadows, right? Because photons have been removed. They have to reappear at higher energy. So you see the same galaxy clusters which appear as shadows at low energy, as sources at high energy. So they have a very characteristic spectral pattern relative to the cosmic microwave background. There are holes in the cosmic microwave background at low energy and sources at higher energy. And of course there must be a frequency in the middle where they completely disappear. This is at 217 gigahertz, independent of the cluster redshift, by the way. So this is why one of these channels of Planck, this one, lies exactly at 217 gigahertz, right? So that this contribution of the foregrounds would not appear there. All right, fine. But this allows you to extract from the Planck data, among other things, galaxy clusters. And you can find many of them, and you can do so in a way that is much more independent of redshift than other ways of finding galaxy clusters. This is just one example. So imagine what happens is, this is what Planck really gives you, right? These are frequency maps. Then of course you have to remove all these foregrounds, and if you are cosmologists, you throw them in the bin. And at night the astronomers would come and take them out of the bin and analyze them in terms of astronomical foregrounds. So among other things, Planck has found a lot of astronomical information, but this is not of our concern here. All right, then once you have extracted everything, you have a map of the cosmic microwave background. Like this. You do the analysis, and from fitting the expectation for the CMB power spectrum to the data, you can extract a whole lot of cosmological parameters very, very precisely. All right, this is what I wanted to tell you about this. Now I would say we again make a short break, right, for you to stretch and walk around, and then in 3 minutes we continue.
Noch zur letzten Vorlesung geschafft.
Ja, das ist toll. Wo sind wir danach vielleicht zum Bahnhof? Schön, dass wir
Ja, ich war die Woche jetzt mal ein paar Tage im Urlaub.
Ja, ich hab's mir gedacht. Und Ihnen herzlich willkommen.
Vorher in Essen seit langer Zeit nochmal. Dann sind wir mein jüngster Sohn ist ja eigentlich Amerikaner, ist ja in Amerika geboren und der wollte unbedingt mal nach New York, weil er meint, er könnte sich gar nicht mehr erinnern an die Zeit. Also da war er noch sehr klein natürlich, als wir das letzte Mal in New York waren. Da waren wir jetzt 4 Tage in New York die Woche, sind gestern Abend wiedergekommen.
Jetzt kommen Sie gleich her, das freut mich.
Ja, bin noch ein bisschen in dem Jetlag, aber ist okay.
Morgens geht's ja.
Gut. Und wie ist es gelaufen?
Sehr gut.
Sehr engagiert. Ja?
Sehr engagiert, kommt nach und auf.
Ja, das war letztes Jahr auch sehr gut. Ja.
Auch hervorragend organisiert. Ne?
Ja, leider das Wetter ist noch nicht so perfekt diese Woche. Da müssen wir noch dran arbeiten.
Haben Sie es auch bestellt? Ne? Das macht nichts.
Und es ist irgendwie 16 Grad heute Morgen, als ich hierher gekommen bin. Am Sonntag wird es besser.
Okay.
Gut.
Oh yeah, the stars
Oh, rein theoretisch kann ich schon meine erste Frage loswerden.
Schieß los.
Wenn man sich die WMAP-Daten und die Planck-Daten anschaut,
Ja.
sieht es ein bisschen so aus, als ob es so einen kleinen Dip bei L = 20 gäbe. Also gut, das ist schon
Ja,
sehr
ja.
Bump-Hunting-mäßig unterwegs.
Ja,
Gibt
ja.
es dazu Theorien? Ich habe irgendwann mal gesehen, in einem
Nee.
Paper hat es was dazu, aber das war...
Also keine vernünftigen, weil das halt in einem Bereich ist, wo die Cosmic Variance total dominiert
ja.
und wo völlig klar ist, wir können uns noch so viel den Kopf zerbrechen, wir werden nie statistisch signifikante Aussagen darüber kriegen.
Okay.
Also es gibt eine Menge Überlegungen dazu. Eine Überlegung war zum Beispiel mal, dass das Universum topologisch mehrfach zusammenhängend sein könnte, ja, woraufhin du halt einen langsamen Abbruch der Fluktuationsamplitude zu sehr großen L hinbekommen würdest, weil das Universum dann selber einen endlich großen Radius hätte.
Ja.
Aber wenn das so wäre, dann müsstest du ringförmige Artefakte am Himmel sehen.
Ja.
Weil du ja sozusagen
Einmal
Lichtstrahlen ums Universum rumwickeln könntest.
Ja.
Siehst du aber nicht.
Okay.
Das heißt, die Konsequenz ist, kann schon sein, dass mehrfach zusammenhängend ist, aber dann ist der Zusammenhangsradius größer als der Hauptradius.
Ja.
Und damit praktisch bedeutungslos. Ja.
Ja.
Ja, ist total interessant. Oder? Okay, ich mache mal weiter. So, let's move on. Huh? Sorry. All right. All right, take seats. We move on. Isn't that nice? Now we have a free coffee and fresh tea. All right. So I think it's not emphasized too much that with the cosmic microwave background observations and the detailed analysis of the fluctuations, cosmology has really changed, has substantially changed. And very much of what I told you essentially in all the lectures so far, namely by how much cosmology has changed and our knowledge of the cosmological parameters has changed since I was in your position, this is due to the precise observations of the cosmic microwave background. We have, of course, several problems, right? And one of the problems is that now we know that there is a huge budget deficit in the energy budget of the universe, right? 70% are missing, so we have to find them. And of course, these boomerang and maxima observations, these balloon observations that I told you about, they produce their first results with a clear indication that the first acoustic peak is at a location that tells you the universe is flat, right? And therefore has an enormous budget deficit. At approximately the same time when the first indications from the supernova observations came, we will talk about this later, that showed that the universe is accelerating in a way, the expansion of the universe is accelerating in a way, such that you could attribute the budget deficit to the cosmological constant, right? But that's a different story. So suddenly, around the year 2000, things fell into place, right? And was very clear there is no way around accepting that the universe is spatially flat and that there must be a finite cosmological constant. Okay, let me introduce cosmological weak lensing, and this means weak gravitational lensing. And of course the idea is that masses deflect light, and since mass and energy are equivalent, this means that any form of energy deflects light. And so imagine you send a light ray, for example one coming from the cosmic microwave background through the entire universe. It will have to pass, of course, through the cosmic structures which are in the process of forming along that time, and therefore the light ray will be deflected any time it goes by a density fluctuation. So this means that there is no such thing as a straight light ray through the universe, right? All of them are deflected. So this is what you expect in an unperturbed, the blue ray, right? Blue ray is what you expect in an unperturbed, homogeneous, isotropic universe, it's just a straight light ray in the corresponding geometry. But then what a light ray really does, and of course this is a gross exaggeration of what it does, right, is that it winds around the expected straight light ray just because it's being deflected all the time. Among other things, this means that what we see of the cosmic microwave background is not the cosmic microwave background itself, but an image of the cosmic microwave background. Right? It's like observing something outside through a non-perfect slab of glass in the window. Right? You know these old windows, right, with a slightly irregular glass. Right? So you see a slightly disturbed pattern outside. That's exactly the situation we are in if we look at the microwave background. And before Planck, it was impossible to see these fluctuations caused by the intervening universe on the microwave background, just because they were on an angular scale below 15 arc-minutes. But with Planck, it's very clear that without correcting for this gravitational lensing effect of the universe, essentially, between us and the microwave background, we cannot expect to derive unbiased cosmological parameters. And with Planck, it was possible for the first time to not only identify the lensing signal in the data themselves, but also to correct the data by the data themselves. Right? How to do this is a different story. Okay, so matter inhomogeneities deflect light. Well, we know that. But then gravitational lensing is strongly astigmatic. In other words, it leads to distortions. Why is that? This is because light rays going by a density fluctuation at a smaller impact parameter are deflected more strongly than light rays going by at a larger impact parameter. Right? So light deflection is differential, and this gives rise to an astigmatism of gravitational lensing. So suppose you visit your optician and you say, give me a lens, and he gives you a gravitational lens instead. You will immediately notice, right, the world won't look very pretty. So now, this means that if you observe any kind of galaxy, distant galaxy far out in the universe, gravitational lensing will give rise to distortion. So suppose all galaxies were circular, right, very nice circles on the sky. Then after gravitational lensing, all of them would be elliptical. Right? Their ellipticity would reflect the distortion. Why elliptical? Well, because that's the lowest order astigmatic distortion you can think of. Right? There are higher order distortions, but we can't measure them. All right. So in other words, gravitational lensing of the intervening universe imprints an ellipticity pattern on the background galaxies. And since the cosmic structures that give rise to this gravitational lensing effect are correlated themselves, the ellipticities will be correlated. Right? So in other words, what you do is you observe a galaxy over here and you see some ellipticity. And of course, from this ellipticity you learn nothing, right? Because galaxies themselves are intrinsically elliptical to some degree. So you have to average over many galaxies, hoping to, in this way, average out their intrinsic ellipticities, so that their lensed, their gravitationally lensed ellipticity would remain. Still, if you see there is an ellipticity of, I don't know, 10% or so over here, you have learned nothing, because you know nothing about the individual density perturbations along that particular line of sight. But now you observe the ellipticity pattern slightly nearby, and you correlate the two ellipticities. Then this correlation of ellipticities will trace the correlation of the matter, and therefore allow you an indirect measurement of the power spectrum of the dark matter fluctuations. And the formula for this is this, right? So P delta is the power spectrum of the density fluctuations, the quantity we talked about yesterday, right? The beautiful, for example, cold dark matter power spectrum we had. This here is the power spectrum of the ellipticities, right? The elliptical distortions imprinted by gravitational lensing on galaxies. Now, of course, this cannot be a quantity of, cannot be a function depending on a wave number, but it can only depend on a multipole order, right? A two-dimensional wave number. So you have a two-dimensional wave number here, but you have to insert a three-dimensional wave number here. Right? So you have to convert these two. But then you just project the power spectrum of the dark matter along the line of sight with a geometrical weight function that takes into account that a given gravitational lens is most efficient if you place it halfway between yourself and the source. And if you put it right in front of your nose, it has no effect. If you put it right in front of the source, neither. If you put it right in the middle, it has the largest effect. So that's taken into account by this capital W function here. All right. So in other words, if you can measure the power spectrum of gravitational lensing imprinted ellipticities on background galaxies, then you have a direct measure of the power spectrum of density fluctuations in the universe. And of course, again, you can instead measure a correlation function, which is the Fourier transform of the power spectrum, as yesterday. Yes, in principle. The problem is the ellipticities imprinted by cosmic gravitational lensing are on the order of 1%. The ellipticities, intrinsic ellipticities of galaxies are on the order of 20%. So this means you need to measure ellipticities extremely well of very many galaxies, of very many very small galaxies, and then you have to average over very many of them before you can expect to get a signal. Another problem is that, of course, this is the astigmatism of gravitational lensing. But if you want to take pictures of the sky, there's a lot of real lensing in between, optical lensing. Right, so you need to understand the astigmatism imprinted by your optical system also extremely well, and so on and so on and so on. So that's a difficult business in detail.
I have a question.
Yeah.
Can this gravitational lensing or the measurements distinguish between clumps of dark matter which are around visible matter versus clumps of dark matter which are just...
This is a very important side effect of gravitational lensing because it is sensitive to all matter, regardless of its form. Remember yesterday we talked about the power spectrum of galaxies, but of course this is a power spectrum of visible matter. Now we get a power spectrum of dark matter. So one of the very important effects is that in this way we can quantify what the relation is between visible matter and dark matter. And the result is it's very closely related. All right, now here are some measurements. Some of them have been published earlier this week, right, on Monday. All right, but this is an older one. And here you see two types of correlation functions. As a function of arc minutes, right, of the angular scale. So this means you correlate galaxies at this position with galaxies some arc minutes away. Right, and that's the angular scale that's plotted on the horizontal axis. You see the absolute value of this correlation function reaches approximately 10 to the minus 4 on the smallest angular scales measurable. So this corresponds to a distortion on the percent level, like I said. Error bars, appreciable, let's say. There are two correlation functions. One is for the so-called E-mode distortion. The other one is for the B-mode distortion. I used the same words already when we talked about the cosmic microwave background fluctuations. Essentially, this means you decompose the distortion pattern or the polarization pattern. Mathematically, they are the same things. They are traceless 2 by 2 tensor fields on the sphere. Anyway, you decompose them into a gradient component and a curl component. And gravity cannot cause the curl component. In analogy to the electromagnetic field, that's called the B-mode contribution. Right? Any pattern that would have a rotational contribution. So we know that if we can measure this B-mode contribution to the gravitational lensing signal, it cannot be caused by gravity, so must be caused by some systematics. So usually in these plots what you see is an E-mode and a B-mode correlation function, and you hope that the B-mode correlation function is compatible with 0. While the E-mode correlation function should of course be much larger than the B-mode correlation function. And that seems to be the case. Now, what do we learn from that? Well, first of all, you can try and fit the shape of the correlation function. Then you can ask yourself, does this agree with a cold dark matter expectation that we were talking about yesterday? And remember in this plot yesterday that I showed you, the gravitational lensing signal was already included. Right? So yes, this is the shape of the correlation function that you expect from cold dark matter. Right? That's the blue curve. But of course the error bars are such that you can imagine this is not very discriminative yet. So what else do we learn? Well, in this plot here, you see on the horizontal axis the dark matter density, or the total matter density, I should say. There's this parameter here running from 0.1 to 1. And then this is the sigma 8 parameter, of which I told you yesterday that it tells you the normalization of the power spectrum, otherwise, in other words, the amplitude of density fluctuations. Right? Now, lensing cannot distinguish between a little bit of matter strongly clumped or a lot of matter weakly clumped. Right? So this would be a little bit of matter strongly clumped. This would be a lot of matter weakly clumped. So this is why there is this degeneracy line in the gravitational lensing results. And it's very hard to break this degeneracy with gravitational lensing. But then you can, of course, combine the lensing signal with other cosmological data, for example, from the cosmic microwave background. And then, of course, the overlap region in the parameter space shrinks dramatically. And you see, again, consistency with the earlier expectation that omega in the matter should be approximately 30% or a bit less than that. So that was the picture in 2008. This is the picture now. Again, you see this characteristic banana. And as you can imagine, a green banana signals there is something unripe in it. Right? So once this banana turns yellow, I think the results will become more credible. So this is again the matter density parameter. This is the sigma 8 parameter. So you see this is now already a section of the previous one. Right? It's approximately this section here, right? Going to a higher sigma 8. So that's one of the latest lensing experiments, KITS 450. It's called KITS 450 because, well, KITS is for kilodegree survey. It's a survey of the sky on 1,000 degrees, 1,000 square degrees. And of these 1,000 square degrees, 450 have already been observed, and that's the result of these 450 square degrees. The gray banana, so it's already a bit rotten, you see, this reflects this experiment here. But this is Planck. This is WMAP. This also was WMAP. So you see how nice the world was and how difficult it gets. So the more precise these measurements get, the more they reveal something that could be a tension between the two experiments that we don't understand. Right? So that's the status with KITS 450. There's a competing experiment, that's the dark energy survey. They have released their data, or part of their data, Monday this week. And again, you see the same kind of plot. Now this is KITS, okay? This one. This is Planck. So this moves the right way, but not quite, yeah.
Both here, and I think on Monday when you were talking about the measurements for H and Hubble constant, you said that kind of a 1 or 2 sigma deviation is conceivably a big problem. In particle physics, we get 1 and 2 sigma deviations kind of all the time. And
yeah.
So why is it a bigger problem in cosmology than?
Because if you trust the 1 sigma deviation, you expect some of the experiments to be above and some of them to be below. And this does not seem to be the case. So even though they are only 1 sigma, right, consistently you find, for example, for the Hubble constant with the local experiments, a higher value than you find with the non-local experiments. Or here, consistently with the cosmic microwave background data, you find a somewhat higher density parameter, somewhat higher normalization of the power spectrum than the gravitational lensing measurements. And this occurs all the time, and this is why we begin to take these 1 sigma deviations seriously. Yeah. Like this? Like that?
I was just wondering, it looks like there could be some structure to the length points, and I was wondering if you expect any structure to this?
Yes, there should be some structure which is imprinted by the geometry of the survey. Right? In fact, what you see is a convolution of the geometrical survey window, let's say the Fourier transform of the survey volume with the power spectrum. This gives rise to features like that. So this part I think we understand. All right, just wanted to show you that this is the situation right now. It's unresolved. This is a pretty picture. I just thought you need to see this. This is lensing reconstructed density fluctuations in the DES survey window. Yeah.
Was the DS plot only the Gauss lensing or the 3x2 lensing?
Sorry, the what?
Is this plot just the Gauss lensing constraints or also the shear and
No, this is exclusively cosmological lensing on background galaxies. So this does not contain galaxy-galaxy lensing. That's a different story. I just didn't want to get into that. All right, now let's talk about the type 1a supernovae. Right? So this is let's just leave gravitational lensing. Right? That's the situation as it is right now, and I don't know how to resolve. I think nobody knows how to resolve these possible discrepancies now. The type 1a supernovae, well, they are a story easily told. First of all, this is a type 1a supernova. How do you know it's a supernova? If you look at this picture for a long time, right, you see this point disappear. If you had looked at it before, that point wouldn't have been there. So that's how you know it's a supernova. How do you know it's a type 1a? Well, you have to take a spectrum and see whether there are hydrogen lines or not. If there are no hydrogen lines, it's a type 1a. All right, what happens in a type 1a supernova, what we believe happens is that you drive a white dwarf crazy. White dwarfs are very sensible inhabitants of the universe. They very, very closely watch their weight. And when their weight starts exceeding 1.4 solar masses, they collapse. And as I said, they are very sensitive. But sometimes they happen to be in a very disgraceful neighborhood, right, where the neighbors just throw their garbage over the fence. And then the white dwarfs have no choice than accepting this mass, and this finally drives them over the limit. So that's a very sad story, in fact. And a very, very anthropomorphic story. So the reason why we still like them is that, first of all, we believe we know the explosive that is then going off, which we believe is a mixture of carbon, nitrogen, and oxygen. Right? That's the composition of the core of the white dwarf. What we also believe we know is the amount of explosive. Right? It's not quite 1.4 solar masses, of course, because that's the whole mass of the white dwarf. What we need to know is what is the mass of the exploding core, which is on the order of half a solar mass. We also know what is being produced by the explosion, namely essentially nickel and cobalt 56. All right, so we believe we know the explosion energy. What we can observe is the flux that we receive from the explosion. And then, of course, you can relate the flux to the energy output and derive the distance. You will get a luminosity distance that way, right? But now you know what the difference is between an angular diameter distance and luminosity distance and so on. So that's not a problem anymore. All right, so in principle, In this way, for each supernova, you can calculate the distance and you know the redshift. And you know the redshift because you need to take a spectrum, and without taking a spectrum, you don't know in the first place whether it was a supernova of type 1a or not. Right? So you need the spectrum anyway. So you have the redshift for granted, and then you can calculate the distance. And this way, you can reconstruct how the distance how distances in the universe, specifically the luminosity distance, increases with redshift. And this, of course, allows you to reconstruct cosmological parameters. This is the kind of data you nowadays get. This is not the distance, but what astronomers call the distance modulus. There's some kind of logarithmic measure of the distance. This time it does in fact increase with increasing distance, so that's a more or less healthy plot. This is redshift, and goes out to redshift 1.4. Which is already quite a lot. Remember what part of cosmic history we cover with redshift 1.4, right? Remember one of the slides from Monday morning? We look over approximately 70% of the evolution of the universe at redshift 1.4. Anyway, so from the run of this distance with redshift, you can constrain cosmological parameters again, right? So here you see again the cosmic density parameter running from 0 to 1.2. Here you see the cosmological constant density parameter also running from 0 to 2. These are enormous ranges, which tell you that the measurement accuracy in this plot is not very high. But nonetheless, in this plane, supernovae give you a constraint like this. In itself, this is of course hugely degenerate. But then the cosmic microwave background tells you that the sum of these two parameters must give 1. So you know that, okay, the supernovae tell you have to be here, but the CMB tells you at the same time you have to be here. Right, and this means that by combination of these two, you can find out that again this is consistent with the density parameter of 0.3, and then you have to attribute all the rest to what may be a cosmological constant or something else. All right, now let's come to the last section about cosmological inflation and dark energy. And without further ado, let me go to this picture here. What is this picture? Well, again, you see the temperature fluctuations on the cosmic microwave background. And this is now an illustration of the concept of a horizon, which I emphasized in the second lecture. So on this map, I have marked a square with 10 by 10 degrees. And I've copied this from this map. And it's, if you look closely, it is in fact a copy of this map, right? So it's not a fake. All right. On this 10 by 10 degree map, you see a circle, and I have magnified this here. This is the horizon size at the decoupling of the CMB. This is the size that we can believe is causally connected at the time of CMB decoupling. Imagine how small this would be on this map, right? It's essentially one of these points. So this means we would understand how you can establish causal connection across a patch as large as this circle. We cannot understand how you can establish causal connection beyond that. But at the same time, if you look at this map, you immediately see that there must have been a process that established causal connection on much larger scales than that. Right? For example, here is a coherent positive temperature fluctuation, which is much larger than this causal horizon. And of course, the strongest argument is, without any mechanism to establish thermal equilibrium between very distant points, why would the cosmic microwave background have the same temperature here than there? And it looks absurd. So what to do? The idea is that very early during its evolution, the universe underwent a strongly accelerated phase of expansion. Let me show you this picture here. So that's the idea, right? The idea is that very early in the evolution of the universe, this was what we now see as our observable universe, right? The blue figure here. The red funnel here, right? This illustrates the size, or this illustrates the radius of causal connection as a function of time, which would go upward. So the idea of inflation is that sometime very early in the universe, everything that we now see as part of our universe was in fact enclosed by the radius of causal connection. And then this was driven apart by the inflationary phase, right? In an accelerated phase of expansion, driven by something or somebody we don't know. And then when inflation ended, this causally connected part, which of course now is much larger than the at that time causally connected region of the universe, reached the size of the universe and remained so until today. All right, this is the only solution we know, essentially. Right? You establish causal connection very early in the universe, but then this is only possible on a small patch of space-time, which means that you will then have to drive this patch apart very, very strongly so that it encompasses the whole visible universe that is now observable to us. All right, how can you do this? Well, you can achieve this, for example, by a scalar field. And then if you, for example, model the Lagrangian of this scalar field in this very simple way, and introduce a sufficiently strong potential for the scalar field, and if you then arrange that the kinetic energy in the scalar field is much smaller than the potential energy of the field, then you can easily show that the scalar field will have an effectively negative pressure. And since pressure is a form of energy, negative pressure acts in a repulsive way and can then drive the universe apart in an accelerated fashion. That's the idea. Inflation is typically quantified by two or more parameters, which are called the slow roll parameters. One of these parameters tells you that the slope of the interaction potential of the scalar field should be small. This means that as the scalar field moves down the potential, trying to reach the potential minimum, it cannot become fast, right? So this means the kinetic energy of the scalar field needs to be small and needs to remain small, right? This is the first condition here. The second slow roll parameter is the curvature of the potential. And this, of course, means that once you have established a situation in which the slope of the potential is small, the slope of the potential should remain small. Right? So this first parameter being very small means you have inflation. The second means you have inflation for sufficiently long time. Otherwise it doesn't work. Right? All right. So the question is, what do we know about these slow roll parameters? Well, first of all, we know that they both have to be very much smaller than one, otherwise, as I said, you would not have inflation, or you would not have inflation for sufficiently long time. The flatness that we observe, right, the spatial flatness in the universe, requires that during inflation, the scale factor of the universe, the observable universe, must have been enhanced by a factor of about e to the power of 60, right, which can of course be translated to a constraint on the slow roll parameters. All right, this would also solve the causality problem, right? But if you drive the universe apart as much as by a factor of e to the power of 60, then you also solve the causality problem that I illustrated in the previous slide. All right. Then, of course, once you have enlarged the universe by a factor of e to the power of 6, you remember what the temperature would do. And it would drop by a factor of e to the power of 60. In other words, in such a universe, after inflation, there is nothing anymore except for the field that drove inflation. So in order to refill the universe with everything we know, this inflation field then has to decay. And we don't know how, of course. Right? We can estimate how it could be in a process that we could call reheating. But of course, reheating must have happened, because otherwise the universe as we know it would not exist. So what do we know about these parameters? Right? As I said, the situation without inflation is desperate, right? Because we cannot understand very simple observations of the cosmic microwave background. The situation with inflation is a little bit better. Remember what I said yesterday about the power spectrum having to increase for small wave numbers like k to the power of n, where n is very close to 1. Well, cosmological inflation, at the same time as it drives the causally connected part of the universe apart, would also increase the inevitable quantum field fluctuations that you have in this area. Right? So the idea is that by this increase by a factor of e to the power of 60 approximately, you would at the same time increase the vacuum fluctuations of the inflaton field to cosmologically appreciable sizes. So this means then that from the fluctuation statistics of the vacuum fluctuations down here, you can calculate what the statistical properties of present day cosmic fluctuations on large scales should be. And you find that this exponent in the power spectrum, right, k to the power of n, should be, if inflation had persisted infinitely long, should be exactly equal to 1. But of course, inflation must have ended sometime, right? Otherwise we wouldn't be here to observe it. And this means that n has to be almost 1. Otherwise inflation would not have been efficient. But not quite. Otherwise it wouldn't have ended. And it has been measured by Planck and other people, Max Planck, right? To be 0.9677 plus or minus 0.006, right? So this is more than 5 sigma away from 1. And this fact is seen as a very strong indication that inflation may in fact have happened. There are opposing views, of course, right? All right, what else do we know about the slow roll parameters? These are the latest results from Planck, of which you can read off that not much. We have an upper bound on the epsilon slow roll parameter. It says epsilon should be less than 0.01. And we have a value for eta for the second slow roll parameter, which, as you see within the error bars, is compatible with 0. But from the fact that its central value is negative, people have started speculating about convex inflation and things like that, and they have wanted to rule out inflation based on this evidence. Right? Judge yourself. I think there are way more papers that deal with the problems that this negative value might cause than reliable measurements. All right, time is up. One problem that we encountered was that, of course, we had to accept that not only do we have dark matter in the universe at an appreciable amount, but also that there is a huge budget deficit in the energy budget of the universe. Right? Since 2000, we know that. The simplest solution for this, to solve this, for solving this energy budget problem, is Einstein's cosmological constant, which we had in the equations from the beginning. From a classical field theoretical point of view, this is no problem at all, because we know since Lovelock's theorems from the 1970s that any metric theory of gravity in 4 dimensions needs to have 2 coupling constants. And one of them is the ordinary Newtonian gravitational constant, and the other one is the cosmological constant. So from that point of view, you would rather have to explain why the cosmological constant should be 0. Nonetheless, right, the value of the cosmological constant is so far off anything else that you would expect from quantum field theory, right, that you want to have, or that another fraction of physicists, let's say, wants to have an explanation in terms of a field. Right? This field has been called cosmono quintessence, gives rise to a modified relation between the pressure and the energy density. Right? For a cosmological constant, this is -1. Now, of course, if you accept a quantum field theoretical origin for the cosmological constant or for the dark energy, you can change that. Then you would get a modified expansion behavior of the universe and so on. So far, I have to say, there is no evidence of W deviating from -1, and there is no evidence for any change of W with time. But of course, these measurements are very difficult. So at the moment, it seems that the very simplest cosmological model, right, based on 3 assumptions: relativity, isotropy, homogeneity, fits all observations in the universe extremely well, including Einstein's cosmological constant. Right? What this all means, I don't know. If you want to change it, you know what you have to change, right? Either get rid of one of these symmetry assumptions or get rid of general relativity. All right, good luck. Thank you.
Any last questions?
Where's the coffee? Yeah.
There's some new experiments planned to measure this slow roll parameters?
The slow roll parameters. Yes, there are additional cosmic microwave background experiments being planned. It's not yet clear which of these will be built. But there will certainly be more experiments that try to find out what the slow roll parameters actually are. Yeah.
So is the hope to get a positive value for this eta?
Yes. So one of the main problems why Planck didn't find anything better is that the polarization signal provided by Planck is much less clear than people had hoped. And the reason is that one of the foreground components, right, namely the dust in the Milky Way, creates a polarization signal that nobody's thought of before. That is because the dust grains that give rise to this emission apparently are not spherical but needle-shaped and are oriented along the galactic magnetic field. So they are an ordered background of dipoles and therefore give rise to an additional polarization that we hadn't known before. And therefore the analysis of the Planck polarization signal is so difficult, and so on and so on.